going to talk more today about systems of linear equations. So we've introduced already what systems of linear equations are and how many different solutions you can have, different variations. So remember that systems of linear equations are a set of equations with the same variables. So here's some examples. 2x plus y equals 7 and x plus 2y equals 9. This set, both have x's, both have y's, and they're both linear equations. Here's another example. Y equals 3x plus 2 and y equals 5x minus 4. They're both linear equations and they both have y's in each and x in each. Now, when you get a solution, if you have a solution, one solution, you'll have it written as a coordinate pair, and it's where they intersect. So where these lines intersect when graphed. You can have a no solution, which remember is when they are parallel to each other. We use a little symbol that means parallel, like two slanted lines. They never touch. So when we graph them, they will never intersect. These will intersect somewhere. So they'll intersect somewhere for one solution. They don't necessarily have to be a perfect 90-degree intersection. They could intersect, at a weird angle, but they're going to intersect in one spot. Then you can have infinite solutions when you actually have the same line graphed. So we have maybe a line here, and then we graph the other line, and it ends up going right over top of it. That means it's infinitely many solutions. All those points on that line can be solutions. So those are the three ways. So today we're going to focus on solve by graphing. So we've got a couple steps that we have to remember. So the first thing is we want to make sure that we put these equations both in slope-intercept form. Remember, slope-intercept form is y equals mx plus b. M is your slope, b is your y-intercept, and then your y and your x are points that can lie on that line that make the equation true. So we're going to change these first to slope-intercept form. So to do that, we want to isolate the y. So we're going to move over the x, both sides. So we end up with 2y equals negative x plus 4. We almost have it along. We divide by 2 every piece. These two cancel out, so we end up having y here equals, remember, a number beside just an x is a 1. So this is a negative half x. And then 4 divided by 2 is 2. So now we have it in slope-intercept form for that one. We're going to do the same thing for the other one. We're going to isolate the y, move everything else over. So minus 2x, minus 2x. So we end up with y equals negative 2x plus 8. Now, the second thing I'm going to do is I'm going to go ahead and graph them. So when we graph, so I'm graphing them in slope-intercept form. We start with our y-intercept. So I'm going to graph the top one first. So we have a 2. So I've already done a graph here. So 1, 2. And my slope is a negative half. Remember, negative means when we start from left to right, start going as a little person, and we walk. When we hit the line, we would actually go down it. So we know it's going to be going in this direction. So here's our first point. To do a negative, we go down 1, remember, rise over run. So we're actually rising a negative 1, so that means down 1, and we're running positive 2, so that's right 2, 1, 2. Down 1, 1, 2. Down 1, 1, 2. If we need to go the other direction, we would actually go up 1 and back, or negative 2. So up 1, 1, 2. So now we've graphed this one, and we'll connect it with the line. And we know this line goes on forever and ever. I'm just doing a snapshot. So now let's go ahead and graph the other one. Y-intercept is where we start. So here was 2, 3, 4, 5, 6, 7, 8. And now we have a slope of negative 2. Negative 2. And if we need to see about a rise and run, remember to put anything as, keep it as a number it is. We can put it over 1. And now we have the rise and run. So we're going down 2, 1, 2, and right 1. Down 2, right 1. Down 2, right 1. Down 2, right 1. And down 2, right 1. Then we can connect. those lines. And notice where they intersect right here is the solution. They do hit each other. That means that point will work to solve both of these equations. So that point is 1, 2, 3, 4, and 0. Okay, so 4 to the x, and we didn't move any on the y-axis, so it's 4, 0. Now the next thing you do is take your solution set and plug it back into your original problem. So we had, use a different color here, so we had x plus 2y equals 4. So this means 4, 0, if I plug it in for x and y, it should be true. So x is 4, so 4 plus 2 times 0, 2 times y is 0, equals 4. Well, 2 times 0 is nothing, so 4 does equal 4. So it works. So let's try it in the other one. 2x plus y equals 8. Well, 2 times 4 plus 0, does that equal 8? Well, 2 times 4 is 8, plus 0 stays 8, is 8. So yes, it works. So we want to make sure that we're plugging back in to verify. Okay? Now, here's the process that we went through. We put both equations in slope-intercept form, which is the y equals mx plus b. We graph both of the lines on graph paper, and we look for an intersection. And then we plug that intersection in, that point coordinate pair, into our original ones to verify that it actually works. Now, there's a quick guide that'll kind of help you to be able to look at problems first before you spend the time graphing to see if it's going to have a solution or not. So remember, we can have a one solution, no solution, or infinitely many solutions. So let's look at this first one. We have y equals a half x plus 3 and y equals 2x plus 5. So what you're going to look at is the slopes. So I'm going to highlight those. So we have a slope here of a half and a slope here of 2. If they have different slopes and also different y-intercepts, we're going to know that this is a one solution. This is going to have a solution somewhere. Then that tells us we can go through the process of finding it. So when we have different slopes and different constant, your constant is just your standalone number right here, and think about that as your y-intercept, we know we'll have one solution. Now let's look at the next one. Again, we're going to look at the slope. Slope of 3 and a slope of 3. Oh, same slopes. Now let's look at the y-intercept, or the constants. -4, -7. They're different, so different y-intercepts, but we have the same slope. This tells me it's going to be a no solution. They are actually going to run parallel to each other, because think about where they are. If you do a little quick thinking about that, if I have, and I'm down here, and I have a -4, and I have a -7, let's say, but I have the same slopes, they're going to run parallel to each other, but they're never going to touch. They have different y-intercepts. So this is a no solution. All right, let's look at another one. Notice this one, one's in slope-intercept form and one is not. So the first thing before we can compare them using this strategy, we need to have them both in the same form. So I'm going to go ahead and put this one in slope-intercept form. So I end up with y equals 4x minus 5. Well, now if we notice and we compare our slopes, we have 4 and 4. So we have the same slope. And now look at your y-intercepts, a -5 and a -5. We have the same y-intercept. So these are actually infinite solutions, because when we graph these are exact same line. They're identical. So we have infinite solutions. All right, so let's do a little challenge one here. So we start here, we have 1 in y equals mx plus b. we have a slope of 1/2, and we have a y-intercept of 5. This one is not in slope-intercept form. This is actually in standard form. So we're going to go ahead and change it. So we want to get y alone, so we've got to move everything else away. Minus 2x, minus 2x. So these are gone. So we're left with 4y equals negative 2x plus 8. And now we got to get y alone more, so we divide by 4 on every piece. So we get y equals 2 fourths, can reduce down to 1/2 x plus 2. Now, if we look at our slope, this is a negative 1/2, and this was a positive 1/2. So these are not the same, so we know they can't be the same line, and they're also not the same, so they can't be no solutions. So the only option when they're different slopes is to have a one solution. So this is a one solution.